fertile that you want to make into fuel. And then also, how do you get it if you irradiate thorium-232 and it ends up making U-233 finally, okay? How do you get it out of here? It's here. You want to put it in here. So you have to have a way to do it, and that's called fluoride volatility. I'll explain what all of this means, but it's a standard process. Okay. The most important thing is that this is a chemical process, so it will not distinguish between the uranium-233 you make and the uranium-232 you make with one in, two out reactions. So there's no way to get around this proliferation resistance. Okay. Okay, so if I were teaching a course on stellar structure, anybody teaching a course on stellar structure starts with the equation of state. In stellar structure, it's almost a perfect gas, so it's really easy to write down. P equals NKT, okay? But we're talking about liquids. So you need something better, something more sophisticated than that. Moreover, why do we use molten salts? Because although it's a liquid, it's an ionic fluid. All right? So in the liquid state, say sodium fluoride, it's a sodium ion and a fluorine ion. There's no bonds to break. It's sodium plus, fluorine minus. So it doesn't matter if I irradiate it with anything, there are no bonds to break. So you can't damage this material. That's why you use this salt. Okay. If you had something else, you could break a bond, and then, you've done something. That's not good. So you want chemical stability at high temperature. These salts have it, because something from the left-hand side of the periodic table combined with something on the right-hand side of the periodic table. That means, by definition, it's very hard for anything in between to get in between, because this is the most electropositive, this is the most electronegative. Okay? So it can do that. It can withstand radiation, has a low enough melting point to be contained in available metal alloys. And as we'll see, it's capable of dissolving sufficient amounts of UF4 and thorium F4 and plutonium F3 if you use plutonium to start it. Once you use plutonium, of course, then once you get to uranium-233, you can run forever. But plutonium is needed as kindling to get the nuclear fire going. So the way to do this properly is to use the thermodynamic potentials. Okay? It gives you all the thermodynamic information that's possible. And the one to use is the so-called Gibbs free energy, which is what you use if you want to have temperature constant and pressure constant. Pressure is something a little less than atmospheric. Temperature is somewhere between, let's say, 800 C or so, or maybe a little more. So what is needed is none of these by themselves are good enough. So you need combinations of them, and the combination that we choose is sodium fluoride combined with beryllium fluoride. So what is the Gibbs free potential of the combination? Well, it's the molar fraction of sodium fluoride times the Gibbs free function of NAF. Same thing of XBF, where these two x's add to 1, if that's all there is. Plus, if they're really soluble and you mix them, they must have entropy change. Okay? The entropy must have gotten bigger, and the Gibbs free energy is related to internal energy by subtracting T times minus S, the entropy. So here's T, and the rest of this is the Gibbs free entropy. All of you who do clean and stuff like that will know this maximum entropy principle. That's a formula for maximum entropy. It goes back to Gibbs, x log x. So since x is less than 1, the logarithm of x is negative, and this means you lower the energy. That's good. Okay? So things want to mix because it lowers the amount of energy that you have in the system. Then you have the interaction between these. Okay? That interaction energy is something that nobody really has a theory for. So in the absence of theory, you rely on experiments or reasonable thought, and you say, all right, the interaction, what is the interaction? It's because a liquid at long range is attractive, but when you try to push the electronic shells together, they become repulsive, okay? Any repulsive energy contributes positive energy. So that's the interaction energy. So to get the right dimensions, nkt, times two products of x's times some function of the temperature. The T0 is just some arbitrary temperature, let's say 1,000 Kelvin, okay? What does this represent, though? It really means that in a liquid, or in a solid for that matter, things are so close, you not only have binary interaction, they can interact with 3 at a time, 4 at a time. So you have to consider all those possibilities, I and j. And you can include enough of them so that you can explain the observation. So it's just purely an empirical thing. And this I, as a function of temperature, you make general enough so that it contains probably the right temperature dependence. So let me summarize this technically. All right? What you want, if something is to be soluble, is that the entropy released by mixing is more negative than the repulsive forces, okay, of the two components. Then you've got a net gain and it will be mixable. It will be miscible. It's soluble. All right? So let me give you an analogy. Most of you are not familiar with molten salts, but the exact same consideration applied to metal alloys. For example, historically it was discovered that copper plus tin, when you melt them, dissolve into each other. When they freeze, they're bronze. And bronze is amazing, thought the old-fashioned way, in that it is harder than either copper or tin. So the combination is better than each one individually. All right? And that's why people who had bronze swords beat the hell out of the people who only had copper swords. And we transitioned from the copper age to the bronze age. Okay? On the other hand, if you combine copper and tungsten, you don't get a soluble mixture because this now dominates that. And if you freeze it, you will get something that in color looks like uniform, but if you went in with a microscope and looked, it would be individual flecks of copper and tungsten and not become soluble. Okay? So solubility is understood at a chemical level through things like this, and whether you get alloys or not. So let's see what this thing does when you apply it to NaF, beryllium F2, at 1 atmosphere. All right? You find if you only had sodium fluoride, you'd need almost 1,300 K to melt the thing. And if you only had beryllium fluoride, you need 830 K or so to melt it. But in between, you see there are local minimas. These are called eutectics, okay, where you get a lower melting point, a minimum. And the interesting thing is, here's two minimums, okay? One is 40-some% sodium fluoride, and the rest is beryllium fluoride, and the other's almost the reverse of that. Those are both good carrier salts because the melting point is only, in Celsius, only about 340 Celsius, okay? And we want to operate the fuel salt at 1,000 Celsius or more. So you have plenty of room where you can operate at. This one's a little better because it has a little more beryllium, which is cleaner, less absorbent of neutrons than this one. But in the middle, you have a maximum. And that maximum is half and half. So there must be some quantum mechanics going on. Okay? What is that quantum mechanics? It's very simple. If I only have one solid, and I model them, one component as spheres, what's the tightest packing you can get? Well, some kind of crystal structure. It's a liquid, it moves around, but it's a solid, it's kind of a crystal structure. Can you put something else in there? No, because it's tightly packed. But if I have a small thing, I can put it in where the spaces aren't. That clearly comes in integer numbers, right? You can put 1 for 4 or 2 for 3, whatever. So that is called, in chemistry, I think, a coordination. complex. So half and half. So when you put something here, it acts like a molecule, a separate molecule, even though it's two different salts. So now I can ask the question, as Oak Ridge did, how much thorium fluoride can I dissolve in this half and half mixture? And here it is, okay? So here's the amount of thorium, molar percentage, and here is the melting point. Okay? Below it, you have different kinds of solid coming out, okay? And again, they're integers if they form crystalline structure. Here's the bad news. So here's our choice. To get enough breeding, we have to have at least, well, comfortably, we have to have about 30% thorium. All right? Fluoride. So here's the freezing point. So you don't want it frozen, you want it a liquid. So you have to be at least 100 or more degrees above that. And that means you're at 880 degrees C. How many metals can withstand 880 C and not be corroded by the salt? And the answer is, conventionally, everyone thinks it's Hassel-AN. This is what Oak Ridge invented to contain lithium beryllium fluoride. But it's only nuclear qualified for 760 degrees. Doesn't mean it can't handle more than 760 degrees, but then you have a long fight with the regulatory agency ahead of you. So you can't use the thing that everybody says you should use. So what should we use? Well, I think I already showed it. We are proposing using an alloy called TZM. M stands for molybdenum, T stands for titanium, Z stands for zirconium. Why molybdenum? Molybdenum is the least metal-like of metals. It's almost a non-metal. And for that reason, it's not easily corroded. Okay? But unfortunately, it's easily oxidized by oxygen. So you better protect it. It's also, since it's almost like a ceramic, it's easy to break. So it's not easy to fabricate. Okay. So people put 1% of titanium and zirconium into molybdenum to make it so you can fabricate things with it. But you still have to deal with the fact that on one side, it likes to be attacked by fluoride. On the other side, it likes to be attacked by oxygen. So what do? Well, I think, but we haven't done this yet. I'm hoping Funtai can do this. I think we can coat it on the inside with molybdenum. Molybdenum is not, since it's 100% molybdenum, it almost has the same coefficient of expansion as 99% thing. So you don't have to worry about it coming off because the temperature changes. On this side, you got to protect it against oxygen. And the two things that can protect alloys against oxygen, either chromium or aluminum. Aluminum has a terrible coefficient of thermal expansion, so probably not usable. But chromium has almost exactly the same coefficient of thermal expansion. So I'm hoping we can get somebody to make us this and test out the corrosion properties. Anyway, that's a hope. All right? So, okay. Now here's a byproduct of using high temperatures. So remember I told you that we want to run the blanket salt at 880 C. Well, when you run it there, at that temperature, you can achieve what is, or almost achieve, the holy grail of nuclear reactors, which is to make water a fuel. You know, if you can make water a fuel, Taiwan is in business, right? We got water all around us, okay? So how do you make water? He said, well, it's very simple. Just do electrolysis. You can show this, I think in grade school they showed this. You put a battery, two electrodes, you put a cup. On one side comes oxygen, the other side comes hydrogen. The problem is after you made the hydrogen and oxygen, you ask how much can you sell for? It's less than the electricity you use to make it. So nobody does it that way, unless you really have terrible electricity, all right? Nobody would do it that way. Why not thermally dissociate it? Well, you need to thermally dissociate at 1 atmosphere. You need temperatures in excess of 2,000 Celsius. Can I think of any metal that can withstand 2,000 C? No, you're almost as bad as fusion. Okay? But can you use a combination? And that is called the Westinghouse hybrid sulfur cycle. Okay. Patents have run out on this, so here it is. What you would like is put in water, come out with H2 and half a mole of O2. So how do you do this? Well, water, as I said, is too difficult to dissociate. How about dissociating the combination where you feed in water, sulfur dioxide, and hydrogen sulfuric acid? Then it turns out you could have it close to the boiling point of this thing, do electrolysis, and you will get out hydrogen because it's easier to electrolyze these three. So you come out with